and I'm going to do the presentation on topic 5, scheduling algorithms. As you can see here, we're going to do a task. So I'm going to present non-primitive priority scheduling. So as you can see here, I prepared a question with processor, burst time, arrival time, and priority. So in order to do this, we're going to create a Gantt chart. So I prepare it. So first of all, we will look at the arrival time of the processor. Which one came first? Should be P1, so it should be P1. And in the middle of it, we should put in the 0. Okay, so the second one, we should look at priority. Which one has the shortest number between all the processors under priority? It should be P2, right? So for P1, we have burst time, so we should put in 5 here as in burst time. Okay, then secondly we got P2, which is the lowest priority of 1. Then afterwards we're going to take 5 and with the burst time of P2, which is 3. So 5 plus 3 should be 8. Next, which one has the lowest number between all the processors under priority, which is P3. Which is P4. So P4 with the burst time of 2. So 8 plus 2, which is 10. Afterwards we have P3 with priority of 4. So 10 plus the burst time of P3, which is 11, which is 1. So 10 plus 1 is 11. So next we have the final, which is process 5. Process 5 with a burst time of 3. So 11 plus 3, which is 14. So you can see here 0, 5, 8, 10, 11, 14. So basically what I do is 0, because previously there's nothing, so we put in 0. And we put in the burst time of 5. So in order to get to P2 here, you know, get that number 8, right? So we take 5, we end it with the P2 burst time. P2 burst time should be 3, so 5 plus 3 is 8. And then for P4, also same. We take a previous burst time 8 with 8, and we plus with P4 burst time, which is 2, so it's 10. And so on, so on. So overall, you can see this. So now we're going to do the completion time. Completion time P1 of completion of P1 is, you can see here, is the completion time. So P1 completion time is 5. So it will be 5 here. And for P2, which is 8, so it will be 8 in here. And for P3, which is 11 here. For P4, we have 10, so we put 10 in here. For P5, we have 14, so we put 14 in here. Okay, so for turnaround time, how do we calculate this? Which is we got to take the completion time minus arrival time. So for turnaround time, what's the completion time for P1, which is 5 minus the arrival time. What's the arrival time? Arrival time of P1, which is 0. So 5 minus 0 is to 5. For P2, 8. So 8 minus with the arrival time. What's the arrival time for P2? Which is 1. So basically 7. For P3, 11 minus with P3 arrival time, which is 2, equals to 9. For P4, completion time minus with the arrival time, which is 3, equals to 7. Then for P process 5, which is the completion time minus with the arrival time, which is 4, equals to 10. So okay, this is the turnaround time. Next, we should do the waiting time. So we have the waiting time. So how do we count waiting time? Waiting time, which is turnaround time minus with burst time. So for waiting time, so we put in the turnaround time, which is 5, right? So 5 minus with the burst time. For P1 burst time, which is what? Which is 5. So 5 equals to 0. Then for P2, we take a turnaround time, which is 7, minus with the burst time, which is 3. So 3. 7 minus 3 should be 4. Yes, 4. So for process 3, turnaround time, which is 9, we minus with the burst time, which is 1, so it's 8. And for process 4, we have the process 4 burst time, which is 2. So 2, so we get 7 minus with 2 equals to 5. Same. Then for process 5, which is turnaround time is 10, we minus with the burst time, which is 3 equals 7. So for waiting time, you can see here this calculation of it. Formula is right here. Turnaround time equals to completion time minus with arrival time. And for waiting time, we have turnaround time minus with burst time. So for final part, which is average waiting time. For average waiting time, you know what should we do? We should take the completion time of this total, right? 5, 8, 11, 10, 14. Then, no, that's wrong. Sorry, my bad. So, for average waiting time, we should take waiting time, which is here. Then we take 0 plus 4 plus 8. So we take it right here, okay? So 0 plus 4 plus 8 plus 5 plus 7. Okay, so basically all of this total, right? Total up. And we divide with, right, how many processors we have. So we have 5 processors, right? So we divide by 5. Okay, so divide by 5. Okay. So answer should be, let me a sec, right? Okay, so 0 plus 4, okay, we say 4, 8, 5, 7. So 4 plus 8, 4 plus 8 plus 5 plus 7 equals to 24. So 24. Then afterwards, divide by 5. So 24 divided by 5, which is 4.8. 4.8. That's average time. So average time for this waiting time is 4.8. So next we should just the average turnaround time. So you can see here, this is our processor turnaround time. So we just ending. So 5 plus 7 plus 9 plus 7 plus 7 plus 9 plus 7 plus 10. Okay, so same as usual. Sum it up. Then we divide by how many processors that we have. So we have 5 processors, we have 5. So then we will do calculation. So 5 plus 7 plus 9 plus 7. So 5 plus 7 plus 9 plus 7 plus 10. Plus 10 equals to 38. So 38, and we divide by 5. Okay, then. So 38 divided by 5, how much you got? 8 divided by 5, which is 7.6. 7.6. 6. Okay. So that's it for my part. So thank you.
Hi Miss and everyone, my name is Ali and I'm presenting about the topic we have choose CPU scheduling. So let's start with the method round robin quantum 2. So this is the question, got 5 process 1, 2, 3, 4, 5. Okay, the first time process 1 is 5, process 2, 3, process 3, 1, process 4, 2, and process 5 is 3. Okay, let's begin. So every time we do round robin, we should start with 0 rival. So now when P1 is preempted, what is the remaining burst time of P1? Even that we have to keep in mind. So the burst time of P1 is 5 unit. 5 unit. So here it has execute for 2 unit of time. So there is a remaining of 3 unit. And that P1 need to execute. Before we place P1 here, let us look at if there are any other processes that has arrived at time 2. So if you see the table, we see that P3 also arrived and have arrived at time 2. After that, there is a new process P4 that has arrived at time 3. P4 and P4 has to be placed at the ready queue. So now let's see what will happen at the next unit of time. So the next time is time 4. So what is the remaining burst time of P2? Let's see, the first time of, or the total burst time of P2 is 3. It's 3 and it has execute for 2 units. Here, so there is a remaining for 1 unit. 1. And P2 has remaining of 1 unit of time which has to be executed later. Let's see if that is the case, or if there were any processes that arrive at time 4. So as you see at time 4, there is another process 5, P5 that has arrived. So P5 also has to place at the end of ready queue, so P1 continue execution. Let's see what happened in the next unit of time. So the next unit of time is 6. And there are no new processes that are arriving. Now the next unit of time is 7 units, and P1 was using the CPU for 5 up to 7. 2 unit, that is a time quantum, is complete. The present process has to be preempted. P1 had a remaining burst time of 3 unit of time, but it has executed only for 2 here, so there is a remaining of 1. Remaining is 1. Okay. So the other process P3, we see that P3 already complete and P4 also completed. Let us just try them out. This one and this one. Let's write them. Mm, and then, so now let's go to the next unit. So the next unit is 10. We see P5 is still within the time quantum, so there is nothing new happening in P5. P5 continuing its resolution, and there are no other processes that arrive. Only P5 is continuing its execution. Let's proceed to the next unit, is 11. So which was a present process need to be preempted. It was P5. So now P5 did complete its execution. No, because the P5 burst time was 3 unit of time, and it has only executed for 2 units. So there is a remaining of 1 unit that P5 has to be executed later. Change to 1. So P5 will be put at the end of the ready queue, and P2 will get the CPU. So this is what our ready queue will look like. So that's all for round robin, and thank you so much.
Hi, my name is Farhan Ashrafi bin Faisal Asfan with ID 12312033029 from D5. Today I will present about Chapter 6 entitled Deadlock. Before we proceed to the question, I will revise about the topic. So the definition is the permanent locking of a set of processes that either compete for system resources or communicate with each other. For example, in real life, we can see in the situation of the lift where people from inside the lift and from outside the lift want to exchange place or movement at the same time. Therefore, the intersection happens. So either inside the lift or outside the lift make movement. Therefore, they can proceed their journey. As well as in economy, where President Donald Trump imposed tariff to China, and also China as a rare earth supplier, as a semiconductor and chip supplier. This tariff movement also makes China to sell the semiconductors. So to the Western Hemisphere, the semiconductors becomes more expensive. So this set of processes is blocked by each other. Therefore, that's how deadlock defined. Now we start with the questions. With 6 processes: P0, P1, P2, P3, P4, and P5, and 3 resources types X, Y, Z, with total instances 11, 7, 6 respectively. So this is the allocation table and max table. So the question is the system safe? First, we need to start with need and available table. To make the need table is max minus allocation. So we start with the first row. 3 minus 1, 2, 1, 2. Then second, 2, 2, 0, 2, 1, 1. P3, 1, 2, 2. P4, 2, 1, 2. And P5, 2, 1, 1. So this is the need table. Now we proceed to available table, which equals to total instances minus total allocation. To find the total instances is 11, 6, 7, 6, and the total allocation is by the resource types. So this is 9, this is 5, and this is 4. So this is the total allocation. So we can find the available. By x, 11 minus 9 is 2. By y, 7 minus 5 is 2. By z, 6 minus 4 is 2. So we have the available table. Now to ensure whether it's safe or not, we start with the safety algorithm, which is need equals and less than available. Start with P0. P0 2 1 2. Available is 2 2 2. So this can be considered as true, and therefore we plus the allocation. Allocation for P0 is 1 1 0. So we update the available, but we proceed for the process of need. So this is process 1 2 2 and 0. Sorry. Update the available becomes 3. 2 plus 1 3. 2 plus 1 also 3. 2 plus 0 is 2. Now it is still true, so plus again with allocation of P1 is 2 0 2. So P2, the need is 2 1 1, and available is 3 plus 2 is 5, and 3 2 plus 2 is 4, and it is still true. The value is true. P2 is less than n, equals to this available. So we also update the available. We plus the allocation of P2. Okay. P3, the need is 1 2 2. The available updated becomes 4 8 4 4. Okay. Then this is also can be true. Then we plus the allocation, the available with allocation. P3 is 2 1. Then need of P4 is 2 1 2, and updated available 10 5 and 5. Then check the value, it is also true, and proceed to P5. Then P5 2 1 1. Wait, before proceed, we add the available with allocation of P4. P4 allocation of P4 is 0 to 1. Then updated available is 7, 6. So this value is also true, so we plus the allocation of P5 is 1, 0, 0. So the total of available is 11, 7 and 6. So this value is same as the total instances of resources X, Y and Z. So before we conclude the safe statement, we arrange the processes. So the processes is not in the same order. For this question, but for other question it can be different order. So P3, P4, P5. So we can conclude that this order has safe sequence, so it can be valued as safe state. So this deadlock can be avoided. So yeah. Hi. Now we proceed to the second question about requesting additional instances. Suppose now P5 requests additional instances 111. Can it be granted? But before we proceed, we update the unit table. And later this line will be changed due to the P5. Now the step 1 is check request whether it's lower than need of P5. So request is 111 and the need is 211. So this value is true, as well as the second step, the available. So one, the whole available is 222. So this is also 2. So proceed to the banker's algorithm. Now we plus the allocation of P5. Which is 100. Then add the request 111 equals to 211. Now the new need, we update the table. New need 211 and the request 111 and minus is 100. Update the table. And lastly two minus 1 equals to 1. So update the new available. Okay, now start with the safety algorithm with the new need table. So the need of P0 is 212, which is false. then P1 to 0, which is also false. Then P2 is 2 1 1, which is also false. P3 is 1 2 2, which is still false. Then P4 is 2 1 2, which is false. Then P5 is 1 0 0, which is true. So since it's true, we add the available with allocation. For this one is P5, so allocation 2 1 1. Then we return this one. But we update the available. So this is 3, this is 2, this is 2. Now it's true. So P1 wait, we update the allocation of P0 1 1 0. Then the available is 2. So P1 is true. So update the available with 202. And 2 1 1. Then the updated available is 6 3 4, which is also true. So at the allocation of P2 is 3 1 0 3. This one which is 1 2 2, updated is 9 4 4, and also true. Then update the available with 2 1 1. Update the available is 11 5 5. So this is also true. So all of these processes are true, so we can conclude that additional request of 1 1 1 from P5 can be granted because the system is in a safe state wait, I forgot the shift sequence. Sorry. Shift sequence is P5, then P0, P1, P2, P3, P4. Then the shift sequence allows the system to be in a safe state. Thus, it will prevent the deadlock. Maybe the deadlock can be avoided. So that's all for me. The second question. Thank you.